This is what the sphere looks like in 3 space, and we're thinking about integrating on the sphere. So the normal to the sphere goes from the center. If you take a line from the center of the sphere to the point on the surface, the normal is a continuation of that line. And that's true at any point on the sphere. The normal points away from the origin and at the point on the sphere that you're interested in. Now let's think of what happens near a little patch like this on the sphere so that we can calculate the area. Well, in the coordinates we're using, the radius, I'm just going to call it A, it's a fixed amount. The angle phi or phi is the angle with the z-axis, with the vertical, and the angle theta is the angle of what happens when you take the projection of the point to the xy plane. It's the angle with the x-axis. So again, this is our base point, and we've projected it down to the xy plane and drawn a line to the origin, and this angle is the angle from the x direction towards the y direction to the line that's the projection of that point. So while we're at it, let's calculate this. The length of this line is the radius times the sine of this angle. You can see it in this triangle here, where this length is opposite phi. So A sine phi is this length here. Now let's think about what happens when we change the coordinates here. If we change phi, we sweep this radial direction down, and so this length here, this length is A, this angle is the change in phi, so we have A times the change in phi, that's this length here. And if we change the angle through this little angle here, the angle with the x-axis, through this little angle here, then we're taking this distance, A sine phi, and we're swinging it over by delta theta, and so this arc here has length A sine phi times the change in theta. And so the product of those two numbers gives us the area in these spherical coordinates.